Okay, guys. Here we are. We're going to work this gas law review. Gas law, basically, the most important thing you can know about gas law is that this is Boyle's, that this is Gay-Lussac, pressure over temperature, and that volume over temperature is Charles. If you can remember that, and you can remember that N in PV equals nRT is number of moles, then you're going to do okay. So, okay. Let us begin. All right. So, explain Boyle's law in words. Write the equation. So that's the first one. That's P1 V1 equals P2 equals V2. And if you don't understand the relationship, then I always say throw in a couple numbers and then change a number, make one higher, and see what has to happen to volume if pressure goes up. And so 2 times 2 is 4, 4 times 1 is 4, that's 4 equals 4. Well, volume has to go down. So as pressure goes up, volume goes down. So what we end up with is this little guy right here, and that is inversely proportional. Inversely, spelled wrong, proportional. Inversely proportional. I think there's an E in there. I don't know. They're not judging me by my spelling. They're judging me by how much chemistry I can get in your heads. And I think so far we've done all right. All right, Charles' law. All right, so Boyle's, Gay-Lussac, Charles. Charles is V1 over T1 equals V2 over T2. And again, you can put numbers in. 2 over 2 equals, and then we're going to raise the volume, and we have to see what happens to temperature. Well, 2 over 2 is equal to 1. To make this equal to 1, I have to have it over 4. So this is directly proportional. That one I think we did actually spell correctly. So as volume goes up, temperature has to go up if pressure is held steady. And that's the thing. The easier way to think about this is as temperature goes up, pressure or volume has to go up if pressure is held steady. Remember, the one variable that's not here, pressure, is held steady. The one variable here, held steady, is temperature. The reason this looks this way is because you can't have a volume that goes down to 0. Actually, this thing would start to do something at the tail end too, but we don't need to worry about that right now. Gay-Lussac, he's that guy. He's P1 over T1 equals P2 over T2. And we figured out that these are directly proportional. I'm not going to do the math again. Directly proportional. I guess I'm glad there's 2 that I can spell and 1 that I can't. So again, as temperature goes up, pressure has to go up if volume is held steady. That's why a can explodes like a. If you've seen really bad accidents where people throw like spray paint cans into a fire, well, that pressure goes up, and it goes up to the point where the aluminum of the can ruptures, steel of the can ruptures, and frequently the contents of the can are flammable, so you basically make a huge napalm ball of yourself when you do that. I don't recommend it, but that's why. And cans of beans, the same thing. If you throw them in the fire, they pop open and stuff like that because you're raising the temperature. The volume is fixed, and the pressure goes up and up until the volume isn't fixed anymore. Okay, so that's all the words I'm going to use about those. Define STP, standard temperature, and pressure. And that is 273 degrees Kelvin. Gas law, everything in Kelvin must be Celsius plus 273 and 1 atmosphere, or 101.325 kPa or 760 torr, however you want. They're all standard here, no biggie. Kelvin equals Celsius plus 273, because that's what I wrote right there. That's what it says right here. That's standard day is 0 Celsius, which is a weird standard day. It's very cold, but whatever. 1 atmosphere equals 101. We just went over this. 325 kPa and 760 millimeters of mercury. And I'm going to add another one, 760 torr, because they are the exact same thing. Write the equation for the ideal gas law and explain what each variable represents. PV equals nRT. Okay, P is equal to pressure units must be matched when picking R. V is equal to volume, and that's in liters. N is equal to number of moles. R is equal to the gas law constant. Gas law constant. So I have two choices. I either pick the gas law constant that matches the pressure that they've given me. If they've given me atmospheres, then I use 0.0821. If they've given me kPa, then I use 8.314. If they've given me torr, or millimeters of mercury, then I use 62.4 for that R. That's what it is. It's a gas law constant. If you don't know what a constant is, someone isn't teaching you math properly. But I believe everybody in this class knows what a constant is. I'm not so worried that you know these units. They're long and tedious, but there they are. The other thing is, if they don't give you a pressure, you can use any of those R's, but just know this: you're calculating your pressure in torr or kPa or atmospheres. Your pressure will match the R that you've chosen. So if you're calculating for P ever, if they want to know the pressure of a gas or whatever, you may have to use the R of your choice, which I always use atmospheres because that's easiest. And then T is equal to temp in degrees Kelvin and Kelvin only. Those are the only degrees we can use is Kelvin, Kelvin, that's it. Kelvin, we're just using Kelvin, no Celsius, always Kelvin. That's what we're going to do. We're going to do a drill. 273 plus 30 is 303 degrees Kelvin. Negative 70 plus 273 is 203 degrees Kelvin. 303 degrees Kelvin to Celsius is, didn't we just say this above there? It's 30 degrees Celsius, right? 198 Kelvin to Celsius, 198 minus, I'm not doing that in my head, minus, not this early morning, 273 is negative 75 degrees Celsius. Negative 75 degrees Celsius. Remember, if it looks like this, it must be changed. If it looks like that, you're good to go. All right. Write the correct equation. Didn't we just do this? All right. P1 V1 equals P2 V2. Charles' law. So Boyle's, V1 T1. V1 T1 equals V2 T2. Don't forget Boyle's, Gay-Lussac, Charles. Boyle's is gay for Charles. Boyle's, gay, Charles. Okay. Gay-Lussac, he's that one in the middle. He's P1 over T1 equals P2 over T2. And ideal gas law is PV equals nRT. All right, here we go. We're solving some stuff. Let's go. Finally, putting this stuff to work. A sample of gas in a steel container has a pressure of 30 kPa at a temperature of minus 100 degrees. Plus 273 is going to make that 173 degrees Kelvin. First thing I'm going to do right out of the gate, because I know that I will miss it and skip it if I don't. So on the first read, if you see Celsius, change it to Kelvins. If the pressure in the container increases to 55 kPa, what is the temperature? So what we have is a pressure and a temperature and a new pressure and a new temperature, or P1 T1 equals P2 T2. So what we have is 30 kPa, and no, you do not have to convert a single thing, at a temperature of 173 degrees Kelvin, goes up to 55 kPa. Then they want to know what temperature this thing is if I compress this cylinder down to a smaller size. So, a little simple math here. 30 divided by 173, enter. 55 divided by, second answer, enter. X equals 317 degrees Kelvin, and I'll round off all that other nonsense. Wait, can you see it there? I'll round off all that other nonsense because they gave me 3 sig figs. I'm going to give them their answer back in 3 sig figs. So here's the answer that I'm using, 317 degrees K. This whole gas law test sheet, life in general, I love gas law. Why? Because we give you the formulas. Everybody does. Even in the AP exam, they give you the formulas. And 2, all you have to do is look and see what you have. If I have a volume and a pressure and another volume, then I know that I am choosing a volume and a pressure and another volume and seeing what happens to it. So I have a 950.0 milliliter sample. The only time I have to use liters is when I'm using this. Volume equals liters, always, always, always. There we go. And then exclamation. Okay, but this doesn't. So I don't have to in any of the other gas laws. I can leave it at 950 milliliters at 2.50 atmospheres is equal to 600 milliliters at X atmospheres. Okay, now if you don't, we want to get away from X. We want X by itself. That means we have to do something with this number to get it away from X. Well, first I'm going to multiply 950 times 2.5 atmospheres. Then I'm going to divide by 600, and what I get is 3.96 atmospheres. It makes sense that it went up. Why does it make sense that it went up? Because the volume went down, and if pressure and volume and pressure and volume and Boyle's law and la-di-da, and you know this. This is inversely proportional. If one thing goes down, the other thing has to go up. If one thing goes up, the other thing has to go down. All right, here we go. 12 minutes in. All right, we have a volume and a pressure again. So 4.31 liters, 0.755 atmospheres. Determine the equals 1.25 atmospheres. And now we have a pressure and we need a volume in liters. Okay, so V equals so many liters. Okay, 4.31, do the side that we know everything for first, and then divide it by 1.25 to isolate V, which gives me a V of 2.6. 2.6 liters. Let's see if this makes sense. My volume went down because my pressure went up. Yes, that is how Boyle's law works. Fantastic. We are cruising right along. Okay. Pardon-moi. Okay. A gas syringe contains 56.5 milliliters of a gas at 345 degrees Kelvin. So I have a volume and a temp, which means a V1 and a T1. Now let's see if I have a V2 and a T2. Oh yes, and I have a V2 and a T2. So what we have is 56.5 milliliters at 345 K. Didn't have to change anything. It is NK, mercifully for me, is equal to, and then they want to say at a standard temperature. So they're saying at STP temperature, which is 273 degrees Kelvin, and we're going to have X milliliters. And we know that if something goes down, these are directly proportional. So if my temp goes down, then my volume must go down if pressure is to be maintained. So 56.5 divided by 345, enter, times 273, enter, is 44. X equals 44.7 milliliters. Yay! It went down just like we knew it would. Okay, gas law is easy, guys. It's so easy. Wow, this is a lot of freaking just regular old gas law questions here, isn't there? Yeah, okay, well, I mean, we'll chomp through them, no big deal, but, you know, I thought there'd be more conceptual stuff maybe on here. Is there no KMT on the review? Did they add no KMT on the review? Molar volume STP, ideal gas law, STP. There's no kinetic molecular theory on here. Okay. Alright. Well, I'm going to keep working till about the 30-minute mark, then I'm going to pause this video and probably make the rest of this, make a whole other part of this video later during my planning. I also need to make y'all some kinetic molecular theory notes or, you know, questions. Okay. A sample of a gas, so I have a pressure and I have two temperatures. So I have a pressure and a temperature. 273 is 773 degrees Kelvin, 773 to 273. 273 degrees Kelvin, and I want to know X millimeters mercury. Alrighty, you know that what we do. 300 divided by 773 times 273 equals 105.9 or 95 millimeters mercury. Temp went way down, pressure had to go down. Went down by a third, pressure went down by a third. That's what directly proportional things do. They directly proportion. Okay. Here I have a volume and a temp. Again, 273 plus 90, 273. Oh, back. 273 plus 98 is 371. Might as well fix that while we're here. And again, a volume and a temp. 42.3 milliliters at 371 degrees Kelvin. Determine the temperature if the volume goes down to 25.8 milliliters because we've cooled the syringe. What is the temperature here in degrees Kelvin? Okay. 25.8 divided by, parentheses, 371 times, nope, clear. 25 point, did you see what I was doing? Jeez. Parentheses, 42.3 divided by 371 Kelvin equals 226, I'm just going to use 3 degrees Kelvin. Temperature went down because the volume went down. If we cooled it, or actually what they said is that we cooled the syringe and then the volume went down to what it is. So, sample of gas has a pressure and a temperature and a different pressure, so 780 millimeters of mercury at 273 plus 297.2, 297.2 degrees Kelvin equals 720 millimeters of mercury. Again, you're just always finding the gas law that matches, you know, the three variables that you have. And sometimes you're going to go, oh, this is ideal gas law, but you'll notice it. While the new volume remains constant, what will be the new temperature of the gas if we decrease the pressure? So if this goes down, that has to go down. So let's see what it goes down to. 720 divided by, parentheses, 780 780 divided by 297.2, parentheses, when did I become a duke? X equals 274.348, blah, blah, blah. Okay, degrees Kelvin. Pressure went down slightly, temperature went down slightly. Shocker. That's what proportional means. They go proportionally. If one goes down a little, then the other one goes down a little. If one goes down a lot, the other one goes down a lot. Okay. I think you get those. I want to... No, Mr. Irwin, don't. Keep going. We have 15 liters and 2 atmospheres, and okay, 15 liters, 2 atmospheres. This is this one. We have yeah. See what it did? See what it did? 15 liters at 2 atmospheres equals 3.5 atmospheres X liters. I was trying to use a different law. You got to use the one that matches. 15 times 2, enter, divided by 3.5, enter, is 8.57. 8.57 liters. So as pressure went up, volume went down if temperature was held the same. An expandable container contains a gas sample with a volume of 15 milliliters, a volume and a temperature. So 293 degrees Kelvin here, 5 milliliters. So 15 milliliters at 293 degrees Kelvin equals 5 milliliters, because we're squishing this sample, X degrees Kelvin, and because we're squishing it, it's going to be hotter. So 5 divided by, parentheses, 15 divided by 293, close parentheses, 97, what? Oh, yeah. Oh, good Lord, 97 point. See, this is what happens. You get in your head, X equals, if the volume goes down and the pressure is held the same, then the temperature must go down. Oh, going crazy here. Going crazy. Okay, let's see what we got. Calculate the volume of gas containing 3 moles of gas at 24, 273 is 297 degrees Kelvin, 7 atmospheres. All right. Pressure, all right, so we're going to use PV equals nRT here because I have a moles and a temp and a pressure. So I have a pressure of 7 atmospheres. And they want to know the volume, so I have to know V. I know N is 3 moles. I'm going to use the gas law that corresponds to my atmospheres, which is 0.0821 liter atmospheres mole degree Kelvin. Yeah, that's right. Okay, and then you don't have to put that. I don't care. And then 297 degrees. I guess I could have just left it up there. And then we're going to say V equals. Remember, we want to get everything on this side away from V. So I'm going to take 3 times 0.0821 times 297, enter, divided by 7, and I'm going to get 10.45. 10.45 liters. Remember, V is always in liters. Liters. There, British liters. Liters? No, that's wrong. Anyway, how many moles of gas would be present in a gas trapped within a 100 millimeter vessel? So I have a pressure and I have a volume. That volume is 0.1 liters. Why do I know this? Because in ideal gas law, you must use liters. Why do I know that? Because of the R constant, they're all liters. So 0.1 liters at 25 degrees, 273 is 298. So we have a temperature of 298. We have a pressure of 3.5 atmospheres equals N 0.0821 and 298. And so we're going to solve for N. Sorry, I'm so messy. It's early and I'm not being careful. 3.5 times 0.1 liter divided by parentheses 0.0821 times 298 parentheses 0.014 moles is what I get. I guess we're going to say that's correct. All right, what is the pressure experienced by 0.70 moles? So I have my N, 0.70 moles. 273, which is a 9, 10, 11, 7, 8, 9, 9, 291, right? So I have my temp, 291 degrees Kelvin, and I'm going to use 0.0821 so I can solve for atmospheres because this is liter atmospheres mole degree Kelvin. And I have a, what do I have? A V of 0.075 liters. Remember, it must be liters, divide by 1,000 if you have milliliters. Okay, and I need a pressure in atmospheres, P, and I'm going to put a little ATM so that I know that my units right there are atmospheres. Man, can y'all even see that? Oh, I hope so. Okay, so what do I got? 0.075. No, quickly, let's do that side first. 0.7 times 0.0821 times 291, enter, divided by 0.075, enter. I get 222 or 223 atmospheres. Oh, wow, that's a big time. 223 atmospheres. That's pretty good pressure there, but I wonder why. Did I do something wrong? That seems wrong. It's a very, very small space. 0.75 milliliters is, oh crap, that's 0.75 milliliters. That's even smaller. Look at me, 7.5 times 10 to the negative 4th. That's wrong. 7, 5 times 10 to the negative 4th, so that's got to be a recalculation there. See? It's kind of helpful to know when you've answered something wrong, and the volume just didn't strike me as being enough to be that much pressure. Or I mean, it struck me as a point. Oops, move that over there. This is 0.70 moles, dummy. Okay, so 0.7 times 0.0821 times 291, and clear. Click. 0.7 times 0.0821 times 291 degrees, enter, divided by let's put this in parentheses, 7.5 times 10 to the negative 4th, parentheses. There we go. How about that pressure? 22298.36 atmospheres. So here's the thing. This is almost a full mole, which would love to live in 22.4 liters. Normally an STP, 0.70 times 22.4 would take 15.68 liters, and you're cramming it down into 3/4 of a milliliter, which if you've ever seen a syringe, it's like that much space. If you cram that amount of gas down to that little tiny space, 0.75 milliliters, it should be 0.75 liters, I'm guessing. You're going to create a whole ton of pressure. So when you get that answer, don't be surprised, don't be shocked, don't be weirded out. 0.75 milliliters is just what we in the industry call very small. Okay. 273, 8, 7, 8, 9, 10, 11, 11, 318. 318 degrees Kelvin. All right. PV, we have a volume, 1.25 liters. We want to know what pressure in atmospheres. We have 0.40 moles, 0.0821, and 318 degrees Kelvin. P equals 0.4 times 0.0821 times 318, enter, divided by, this should be more reasonable, 1.25, 8.35 atmospheres. Yep, 1.25 is still a lot smaller than 22.4 liters. Okay. Where are we at here? Oh, 31 minutes. Okay, we're gonna, let me do, yeah, this one last one. 8 moles. Okay, so we have 8 moles. 273, that's 323, 323 degrees Kelvin. We have 4.2 atmospheres. We need a volume, so we have P and V and N and R. And now we just need a V. So 8 times 0.00821 times 323 divided by 4.2 atmospheres. 50.5 liters volume equal. That makes sense. 8 moles. 4 atmospheres. Okay, gang, I'm going to pause this one before we get to AKS4H using mathematical and computational, whatever that is. And I'll get right back to you.